So MATH30. The first quiz was due on Canvas on Wednesday, and I'll be grading that soon. And then you should have completed exam 1 on WebAssign. Okay, I will be first goal of mine is to respond to all of the emails, so post all of our recent meetings and today's, and then make some homework for you and update your gradebook. So I will just transfer these homework scores and exam score to Canvas, and then I will grade the quiz, and I will try to also put comments on the welcome back quiz soon, but right now we need to catch up on homework. All right, we're going to finish chapter 2. And so the only last comment I have is someone already wrote to me that they misread the problem on Canvas because it was difficult to read. So if something happens where it was hard to read the problem or write the problem because it was online, you can let me know. It's 2.8. We were talking about a function being differentiable, and I want to list some places where a function is not differentiable. We'll go through one specific one. Okay, so at corners, at discontinuities, and at cusps. So if it goes this way, or I'm going to draw some function f of x. We're going to go up and down. Jump to a open spot here, fill in there. We'll do a cusp, go down. Also going to add this part. So that would be a corner right there. This discontinuity is a place where the function is not differentiable. And a spot. this would be because another. So you can take the derivative up, like closer and closer to the spot, but not right there. Would this be x equals 0? Or right here where there's a jump, or right here where there's a cusp, or at this place here where there's a vertical asymptote. So I did pick out the absolute value of x to talk about. I wrote a whole lot of notes on it, and I feel like it's a bit much. So we'll summarize the important parts for this function. So absolute value of x is x if x is greater than or equal to 0. Or negative x if x is less than 0. So I want to start off with mentioning that f of x is continuous for all values of x. But it is differentiable for all values of x except for that part there at x equals 0. Oh, okay, that's not good. So we'll do the continuous part. I have it's continuous at, well, it is continuous for all x values, including x equals 0. So I just put that part down. Continuous at x equals 0. Since the limit as x goes to 0 of the absolute value of x equals 0. Put 0 as your output, and that is also the output for the function f of 0 equals 0. I'm going to skip the whole proof. We're going to just go to just x equals 0, and then find the derivative. Let's go from the left and then from the right. So approach. Put h. x plus h, subtract f of x, and it's over h. I think I'll stick with this. I'm kind of jumping around. So h goes to 0, and it's some number less than 0. And we have this as the negative of x plus h minus a negative x over h, since we're on the left side of 0. Minus negative x over h. Okay. Negative x, negative h plus x. Let's see, negative x, oh, plus x. Okay, we've got the limit as h goes to 0 of negative h over h. And that's the limit as h goes to 0 of negative 1. Okay. So just to start over, but we're going to just have the limit of h going to 0 from the right of f of x plus h minus f of x over h. This is some number on the right side of 0, some positive h, and also a positive x. So this is a positive value. The absolute value will just be x plus h. And same for this. Absolute value of x will be x. The limit as h goes to 0 of h over h. So this time I got positive 1. All right, since the limits are different, the derivative, which this was the derivative, let me see. The derivative of 0, and then we did it from the right and from the left. They did not match, which means it does not exist. So f prime of 0 does not exist. All right, last thing I want to say about this is to quickly draw the graph of f prime of x. And let's use a little side sketch. Okay, so here's the original function, which was the absolute value of x. F prime of x is the slope of the tangent line at some value x. At these x values, the slope of the tangent line would be -1. So from -infinity up to x equals 0, but not including -1. And the slope of the tangent line for x values that are above 0 would be a line like this with slope 1, except we can't take the derivative at 0, so that's empty. It goes over to the right like this. All right, moving on to some kind of word problem. So we have a function, and I just want to talk about what the function says in different situations. I think I called it P of T represent population size. Since, let's see, population size where T is time in years since 1900. Okay, one moment. So we're going to say, what does P prime of T represent? It is a rate of change. Let's see, so it's the rate at which the population size changes, but I'm going to say increases or decreases. Okay, so the rate at which the population size is increasing or decreasing with respect to time. I think I said just with respect to time. So, well, let's go for this part. What does the p prime of 30 mean? Also, note that t equals 0 corresponds to the year 1900. Okay. P prime of 30. It is, or it says, oh, let's put this equal to something. P prime of 30 is equal to 6,353. Okay, so P prime of 30 is 6,353. So in the year 1930, the population size increases, so this is a positive output. At a rate of 6,353 people per year. And I made up a little sketch of what this might look like. So we will draw P of t, which is just a function for the population size. So it's still the same idea, but just a pretend function where you have some population here at t equals 0 or 1900. And let's say we just start to grow exponentially. And over at 30, we find the derivative, or the slope of the tangent line. That is the derivative. The slope of the tangent line at 30. So some tangent line right about there. And so I just labeled that P prime of 30 is the slope of the tangent. So it'd be a very steep slope of 6,353. Cool. That's the end of chapter 2. And again, we will have some chapter 2 homework up soon to finish the section. I won't assign too many problems, but we do want to practice a little bit for each topic. I would like to start chapter 3. and not keep the class over. Okay, so timer set for 2:45, and we'll see how far we get through the notes for this chapter. So before we continue on, I just want to mention that with everything going on, switching to online, and also just my personal issues with the internet, I have help from other people. I have a list of topics that need to be covered and a few things that we can skip. And I will, plan for us to have practice chapter 5, so that way when you get to Calc 2, you'll be prepared. So let's start chapter 3. Let's start with a reminder that f prime of x is a function. That gives the slope of the tangent lines to f of x at any point. So I will put up also the definition for f prime of x, and then this chapter we start to find some properties and rules that we can use to get the derivative quickly and not do the limit every time, But if in doubt, just go to the definition and work through the problem. F prime of x. So the limit as h goes to 0 of f of x plus h subtract f of x divided by h. And some notation. F prime of x. Maybe we'll back up. So let's have some function f of x equal to y, or y equals f of x. Okay. So f prime of x is the derivative of y with respect to x. Read dy dx. So if someone says dy dx, take the derivative of your function with respect to x. Also, f prime of x is the derivative with respect to x of f of x. d dx of f of x means take the derivative with respect to that variable x for your function in x. There's a couple of these, so I picked one more. It really just depends on your teacher, what they like the most. So I have f prime of x equal to y prime. So y prime, or the derivative of y. And y is some function in x, so take the derivative with respect to x. And I say that because you may be in a class, or maybe even in this class, we'll get to functions that have like multivariable functions, more than two variables. So it depends on which one is, which one we take the derivative with the focus on a certain variable. Let's keep it simple. So a constant function is going to be our first rule. F of x is some number c. Take the derivative with respect to x, which there is no x there, it's just a number. And we will show that the derivative of a number is 0. Or the derivative of the constant function is 0. Take the limit as h goes to 0. Well, let's introduce it. Let f of x equals c. H goes to 0. F of x plus h. Subtract f of x divided by h. Here's your function, which is c. So there's no place to put in your variable. You just put a c down. The limit as h goes to 0 of c minus c over h. And let's try some. So example where you have f of x equal to 205. Okay, f prime of x. The derivative of the function f will be 0. All right, let's do y equals 7, dy dx, the derivative of y with respect to x will be 0. It's just some number right there. Always going to have a 0 as the derivative when your function is the constant value. I think we can go on. So the power rule up here. f of x is equal to x to some power n. I didn't write down if n has to be a specific value. I'll check it later. So the derivative would be f prime of x. And multiply n with x to a power of n minus 1. I have f of x equal to let's do x to the 10th. Okay, f prime of x be 10x to the 9th. So I will walk through this proof and more examples after that. So prove it. Okay, so just introduce the function. Take the derivative. We want the limit as h goes to 0 of f of x plus h is f of x divided by h. And then get everything in. X plus h to the power of n. Minus x to the n. Now I'm realizing, oh, oof, I did this for a specific function. So I did it proof for an easier version. This is going to be a little bit more, it's easy, you can do it, it's just a little bit more than I wanted to do today. So we're going to go back and let f of x equal x. So x with a power of 1. We're just going to focus on n equals 1. So derivative of f of x equals x, and we have the limit as, we have the definition, and then we're going to put in a power of just 1. So that's going to make this less of a headache. This has just power 1, and this becomes really easy. X minus x leaves this h over h, and h over h is 1. The limit is 1. I'll walk through what you would do with that rule that we wrote down. So that's the end of the proof. So x has power 1. So bring down 1, multiply it with x to the power of 1 minus 1. So 1 times x to the 0 is 1. Okay, so practice problems. We have something like over x to the 7th. So for a lot of these, you want to write them to x to some power if you can, and then you can use the power rule. So rewrite your function, then take the derivative. Bring down -7, multiply it with x to the power of -7 minus 1. And usually you want to rewrite the problem so it's easy to read. So -7 over x to the 8th. Oh, actually, we'll rewrite the problem just on the side. So x with square root, the root goes in the denominator of your power. So we would bring down 1/2 x to a power of 1/2 minus 1. So 1/2 times x to the -1/2. Which we can make look a lot cleaner if we write 1 over 2 root x. Just bring that to the denominator. I'm going to change it back to a root. One more. F of x equals, let's do this. Let's let y equal the cubed root of x to the 5th. So this would go in the numerator, the root goes in the denominator, power of 5/3. You could write y prime or dy dx, the derivative of y with respect to x. Take the variable x and use the power rule. 5/3 times x to the 5/3 minus 1. So it'd be a power of 2/3. Just checking this, add a 5/3, and so we get a positive. Yeah, it's cool. Just make sure. How are we doing? Awesome. We have lots of time. Another rule. Next one is called the constant multiple rule. Let's get it over here. No. You'll write the derivative with respect to x dx of c times f of x. You can bring out the c and have c times the derivative of f of x. All right, I think we just want to work on these. I wrote that our function is y equals 7 over x. I would rewrite this, and then we would have a power of -1 on x. So that I can use the power rule. 7 will be multiplied with the derivative x to the derivative of x to the -1. So we're taking the derivative of y, or derivative of y with respect to x, which would be 7 times, bring down -1, x to a power of -2. And we want to rewrite that to look a little nicer, easier to read. I've got -7 over x to the +2. Yeah. Oh man. Practice. Next one. Let's do g of x. Equal 10 root x. Find g prime x. So take the derivative of g with respect to x. Let's rewrite it first. Rewrite. It's 10 times x to a power of 1/2. And then when we take the derivative, we'll have 10 multiplied with, so kind of brought that out, and now take the power rule, bring down 1/2 x to a -1/2. And we had this 1/2 times 10 will be 5, and it's over x to a power of 1/2. I think it would look a little nicer if you had 5 over root x. It doesn't really matter that much though. Okay. Next rule is for sums and differences. By the way, now that we're using these rules, you can, of course, use them on your homework and exam to skip doing the whole limit process. So if you have some functions, the derivative with respect to x. Of f of x plus f of x plus or minus g of x. Is to take the derivative of f of x, add or subtract the derivative of g of x. Let's call this function h of x. And it is x squared minus 2x plus 5. And h prime of x. So the derivative of the function h with respect to x. So we will do them like piece by piece, and we can subtract and add as we go from this rule. First one has a power rule, 2x with the power 1 minus 2 times the derivative of x with power 1, so 1 times x to the 0, which is going to be 1. And you have a constant at the end. We talked about this. The derivative of a constant will be 0. So in the end, I have 2x minus 2. Next function is f of x equal to 3x squared minus 2 over x to the 5th. And add, we're going to put 10 cubed root x. Let's make it 9. 10's fine. 10 cubed root x. And that's good. Take the derivative. Let's rewrite the function first. Minus 2x to the negative 5 plus 10x to the power of 1/3. First part here, we will do 3 times the derivative of x squared. So we'll have 2 times 3, x to the power 1. Okay. We'll put some of what's going on down. Negative 5 times negative 2 So it's negative 2 there. I brought down my negative 5 here, and then x has a power of negative 5 minus 1. This piece plus 1/3 times 10, or 10 times 1/3. And then the x, write that down, x has a power of 1/3 minus 1. make our answer look a little better. So we will write f prime of x is 6x plus 10 over x to the 6th. And I'm just going to leave it as 10/3 x minus, let's see, 1/3 minus 3/3 will be a negative 2/3. Sweet. Okay, cool. Okay, that part, and we're done. All right. Let's get through this example. We will find the equation of the tangent line to f of x. It equals f of x is x cubed minus 3x squared plus 1 over root x. At the point 1, negative 1. Okay, so the equation of the tangent line, first we'll get the slope for that equation using the derivative. And then we'll use the, I think it's called a point slope formula for the equation of a line to get the whole tangent line. Start with the derivative. Let's see, x equals 1. This is an x, and it's a y. F prime of 1. So the slope of the tangent line to f of x at x equals 1 will be. Well, let's back up. Let's find some scratch work. Let's just do the derivative, and then we'll put in x equals 1. So power rule here, 3x squared minus 6x to the first. And this is a x to the negative 1/2. So we want to subtract 1/2 x to a negative 3/2. Just writing this a little nicer. me check. This would be.
Professor, wouldn't that be a square root, you know?
Oh, you're right. Yeah. Thank you. I want this denominator here and that power. We'll put it. We could put it here. It's fine. And let's do f prime of 1. 3 times 1 squared minus 6 times 1 minus 1 over 2 square root 1 cubed. Got it. Let's just do this. 1 squared is 1. That makes this 3. This is 6. 1 cubed is 1. Square root 1, which is 1. So this whole piece here is 1. And you subtract 1/2. We have negative 3 minus 1/2. Get a common denominator, negative 6 over 2 minus 1 over 2. It's negative 7 halves. So I don't know if I want to write the whole thing. The slope of the tangent line is negative 7 halves. And the equation of the tangent line is going to have like the basic equation of a line with this specific slope. So we'll go y minus y1 equal to the slope times x minus x1. Your function f, we'll draw a little kind of sketch. Your function goes through 1, negative 1. So this is definitely not the same function, but let's just pretend like you've got a function and it goes through a similar point. Like so this function f of x, it goes through 1, negative 1, and the tangent line also goes through that point because it's sitting right there, going through that point and tangent to that curve. So f prime of x also goes through the point 1, negative 1. So it's a point that we can use for our x and y values. Negative 1 for y, and x was 1. Negative 7 halves x plus 7 halves. And we want to solve for y. See if you subtract 1, you add 5 halves. Did it come out quite? Yeah, that looks good to me. So it was the equation of the tangent line is negative 7 halves x, add 5 halves. And that's it. We've got a few minutes, and these I would say are two side notes. We'll bring up one, save the other for next time. So a note about horizontal tangents, and then next time we'll come back to normal lines. So from what I can remember about normal lines is it probably came up in Calc 3, where you do things in 3D. You have kind of different vectors going on, traveling along a curve. You'll get there. And that's it. Out of a lot of math classes, I didn't use normal lines very much. Anyway, we'll do that next time. So we want to finish with horizontal tangents. Okay, so horizontal tangent lines. Okay. To OCCUR, where the derivative is 0. So when f prime of x equals 0, the tangent line will be horizontal. When this comes up is some kind of question like a person throws an object into the air. And, we practiced this in a math class. I practiced it a tiny bit in physics, the few physics classes that I did take. And you have some person and let's say they have a rock and they throw it. And you were trying to solve the problem. A part that is useful is right here. When the tangent line is flat, when f prime of x equals 0, and you've reached the highest that the object can go. Let's call this, like usually this is time, t. And we'll call that a specific t, like t naught. When the object reaches its peak is when f prime of t naught equals 0. So sometimes they'll tell you like a max height of 200 or something like that, and you'll know this number here. You can use that. Okay, let's wrap it up. That's the end of class. I'm working today on loading up our meetings and getting them posted to Canvas. So we'll get back to 3.1 notes next time. I'll try to get these notes up today or as soon as possible.